In the next few videos, we're going to talk about some extensions to the idea of integration or integration process. So far, when we've studied integration, the definite integral, we always defined it as a function that's defined on a closed bounded interval, say from a to b. And that was our definition of the Riemann integral. But there's a lot of situations where you want to integrate, you want to have some kind of integration process that doesn't exactly fit that scenario. And there's two major ways that this comes up. So one way that this can come up is you want to integrate over an interval that's not bounded. So it's not from 0 to 1. It's not from 3 to 5. In other words, you want to integrate out to infinity, or out to minus infinity, or maybe you want to integrate over the entire real line. And this is actually a very common occurrence. It happens in a lot of different applications. And we don't really have a definition for that. The other thing that can come up that can kind of make things a little different is if you're integrating a function and it's discontinuous. Now, we've already talked about the fact that if you have a jump discontinuity, that's really not an issue if you have just a finite number of them, because you can just split the integral into different pieces and then just integrate each piece. But if you have some kind of discontinuity that's a little more serious, like an infinite discontinuity is very common, then you can't really do that, or you can't really make sense of it right now. And that is also a common occurrence. So what we're going to do is take the definition of integration that we have so far on a closed bounded interval, and we're going to try and extend it and define, well, what would it mean to integrate over an unbounded interval? What would it mean to try and integrate when you have this infinite discontinuity? And in all the cases, the idea is that you try and approach the problem. So for instance, if you're integrating all the way out to infinity, you say, well, I can't integrate all the way out to infinity, but I could integrate all the way out to 1,000,000 or 1,000,000,000 or 1,000,000,000,000. So you imagine some very big number. It's a bounded interval, but it's a very big interval. And then you say, well, why don't I just let the right endpoint approach infinity? In other words, I'm going to take a limiting process again. So it's the idea of approximating and then defining something in terms of a limit, something we've come across over and over again. When we were defining derivatives, when we were defining integrals, we had the same idea. And the same thing is true of an infinite discontinuity. If it occurs at a point, you can get really close to the point and say, well, really close to it, it's not a problem. I could integrate up to there. What if I just try and get closer and closer to that problem point of the discontinuity? Could I then take a limit and see what happens? And these are called improper integrals. And I don't really like this name because improper suggests that there's something wrong with them. You know, they're not proper, but it's just a name. So I wouldn't read too much into that. Now, there's a lot of different ways that you could approach this problem. And in fact, the type of integration that we study in calculus classes that we usually teach calculus students is just one of many different ways you can define integration. And many of these other different ways of defining integration, you wouldn't have these kinds of problems, or you would be able to accommodate it. But the definite Riemann integral that we studied, it doesn't quite do that. So we do have to try and take into account what we're going to do in these situations. And the names for these are not very original. They're simply called type 1 and type 2, respectively. So let's just get in and do some examples. Let me first go over kind of the situations where type 1 would occur. And actually type 2, it's very similar. So the types of situations where type 2 would come up is a similar kind of idea. So probably the most common or most commonly cited and familiar example of one of these improper integrals is in statistics. When you're studying probability, there are continuous probability distributions. You can think of, for instance, the normal distribution or the bell curve. And these are defined on the entire real line. And so the area under the graph of this distribution function, you want to think of as adding up to total probability 1. But then that means you have to integrate from minus infinity to infinity. So that's a very common example. And in order to calculate things like averages and standard deviations, you also have to use the improper integral. Same kind of thing happens in many situations in physics and chemistry when you're finding the average speed of molecules in an ideal gas, or the average life of an atom in a radioactively decaying substance. You have improper integrals. Then there's cases where it's not a direct application, but it's a situation where mathematically these things come up. So oftentimes you want to do a change of variables. So you transform a problem from one variable to another, and it's algebraically easier, or you can do it where you couldn't do it before. But in the process of doing that, you make a bounded interval into an unbounded interval. Well, what are you going to do then? So you still have to integrate, but now it's unbounded. So it can come up from a change of variables. There's also a lot of special functions in math and physics that are very, very useful, that are defined in terms of these improper integrals. The gamma function, which generalizes the factorial function, is probably the most well-known example of that. And lastly, if you go on to study differential equations, there are some transforms that are used to study differential equations that, again, transform one type of problem into another. And these transforms take a certain function and make it into another function. The two common ones are called the Laplace and Fourier transforms, and those are also defined in terms of an improper integral. So this is not an abstract, esoteric idea that doesn't ever come up. This is a very useful, common idea that's used in math and physics and science. Okay, before jumping into the definition, what I'm going to do is start with an example to motivate it. And it's going to be based on this idea that we've talked about before, that if you don't exactly know how to define something, think of an approximation to what you think it should be defined as. Well, it should be something close to this. And then think about what a better and better approximation would look like. And then if there's an appropriate limiting process or limit that you can apply, then simply define the value as the limit of those approximations. So here's the problem. We're going to find the area of the region bounded by the graphs of y equals 1 over x squared, the vertical line x equals 1, and the x-axis. Now, if you think about this region, before I even draw it, just picture it in your mind. This region is not a bounded region in the sense that it has infinite extent. It goes off forever in the positive direction. So at first you might think, well, if it goes off forever, it must have unbounded area. That's not exactly the case. So what we're going to find out is that you can have regions that extend infinitely far in a certain direction, and the area might be infinite, but the area might be finite too. It might actually be a definite area. Again, infinity is a weird concept. It takes some getting used to. There's a lot of kind of counterintuitive things that happen with infinity and with infinite processes. And this is one of them, the idea that you can have a region that extends out forever but still has finite area. So let me draw this particular region, and then we're going to set about thinking about how we could get a hold of what the area under it should be close to. All right, so this is the region that we're thinking about, shaded in blue here, and actually it's probably the graph falls off a little bit quicker than I've even drawn it here, but still it has the same general features. And so let's think about what an approximation to this might look like. So a good approximation might be, well, we can't go all the way out to infinity. Why don't we go out to 100? Let's see what we get if we do 100. The integral from 1 to 100. Now notice here, if we're integrating out to some large number, if we start at 1, then this would just be like the area under the curve of a closed bounded interval. So we can integrate, say, from 1 to 100 dx over x squared. Now, the integral of 1 over x squared, that's x to the negative 2, so it's x to the negative 1 over negative 1, so it's minus 1 over x evaluated from 1 to 100. And that turns out to be, well, it's 1 minus 1 over 100. So it's 99 over 100. Okay, so you could say, well, that's great. Why don't I get an even better approximation? Why don't I integrate from 1 up to 1,000,000? And you might even start to see the pattern here about what's going to happen. Again, I'm going to integrate minus 1 over x from 1 to 1,000,000. And so this is going to be 1 minus 1 over 1,000,000. So I'm going to get 999,999 over 1,000,000. And at this point, you can probably see what I'm going to get if I just integrated up to an arbitrary number. So instead of 100 or instead of 1,000,000, in general, if I integrated all the way out to t, the integral from 1 to t would be minus 1 over x, evaluated from 1 to t, which is going to be 1 minus 1 over t. So 99 over 100, 999,999 over 1,000,000, 1 minus 1 over t. So it makes sense then to define the area of the region as what this 1 minus 1 over t is getting closer and closer to as t goes to infinity. So it makes sense. And let's see then what that would look like. So we would get we would say the integral from 1 to infinity. Now it looks a little weird, the notation, that's how the notation works. Instead of a number as the upper limit, we have an upper limit of infinity. So we'd say the integral from 1 to infinity of dx over x squared is equal to the limit as t goes to infinity of the integral from 1 to t of dx over x squared, which is the limit as t goes to infinity of this 1 minus 1 over t. And of course, as t goes to infinity, 1 over t goes to 0. So that just means the value of the limit is 1. And that is that's the value of this improper integral. So we would say that the integral from 1 to infinity of 1 over x squared dx is exactly equal to 1. And we would also think that the area of that infinite extending region above is also exactly equal to 1. Okay, so with this example, I think we're in the place to actually write down a definition. So let's write down the definition. This is one specific case, but there's different cases that can come up, so we have to be a little bit careful. All right, so this is the definition of improper integrals of type 1. And we'll deal with improper integrals of type 2 in the next video. First case is going to be if we want to integrate out to infinity. And the second case will be if we want to integrate out to negative infinity. And then the third will be if we want to do the entire real line. Okay, so let f be a function defined from a out to infinity. And suppose that the integral from a up to t exists for every t bigger than a. Then we're going to define the integral from a to infinity to be the limit of these integrals from a to t, provided that limit exists as a finite number. Now, to be clear, there's nothing that says that this limit has to exist. The limit might be infinity, so the area just might blow up to infinity. Also, the area might oscillate around. So there's nothing that says that this particular limit has to exist. If the limit does exist, we are going to say that the integral converges, and if it doesn't exist, we're going to say that it diverges, but we'll get to that in the comments later. All right. The case where you integrate out to minus infinity is almost the same. You just kind of switch everything around. So, in fact, you should almost be able to write down the definition for this, but I will go ahead and write it down. All right, so now we have to decide what we're going to do about minus infinity to infinity. And what we're going to do here is we're going to split it up. So we're going to take some point between minus infinity and infinity and say, let's just integrate from minus infinity up to here, and then from there up to infinity. In other words, we're going to get a sum of two improper integrals, one from part A definition, one from part B definition. Now, there's a little subtlety that comes up here that I'll address in the comments, but see if you can think about the subtlety before we get to it. There's something that you have to check with the definition. So we're going to define, let f be a function defined on minus infinity to infinity. Then we're going to define the integral from minus infinity to infinity to be the integral from minus infinity to a plus the integral from a to infinity, where a is just some real number. Okay, so what is something that's interesting about this definition? I'll give you a few seconds to think about that. So first thing is, these two integrals have to exist. In other words, this is not going to make much sense. If one of these integral from minus infinity to a or a to infinity, if those don't exist, then this is not going to make sense. But the other thing is, I didn't tell you what a was. I mean, somebody could choose a to be 0. Somebody else could choose a to be 1. Somebody else could choose a to be pi squared over 6. So, are we all going to get the same answer? Maybe it's not clear immediately. It turns out that you will always get the same answer, but that's something you have to show. I'm not going to go through it. You're just playing around with limits, but you might want to think about why that is, that it doesn't really matter what intermediate real number you choose to split this up at. Okay, so I do need to put here, provided both limits on both improper integrals, I'll say, on the right-hand side exist. Okay, so there's a few comments that are important. Number one, I already mentioned, if one of these improper integrals exists, we say that it converges. Otherwise, we say that it diverges. Point number two is what I said about the integral from minus infinity to infinity. It can be shown that the definition in part C is independent of the choice of A. So just to be clear exactly what that means that if you choose a certain value of A and it converges, then any other value you choose, it will also converge and converge to the same number. It'll be the same value. And if your choice of A makes this improper integral diverge, then any other choice will also have divergence. It might not be the same one of the two, but one of those two will diverge, causing the entire thing to diverge. So it'll always converge or with both of them, or diverge with both of them, and if they converge, they'll agree on the same value. Now, the last thing to note is, and this is a common mistake a lot of people make, the integral from minus infinity to infinity, and I'll just put here as defined in part C, so the way that we have just defined it, is not the following. Okay, this is not the same thing as taking the limit as t goes to infinity of the integral from minus t to t. In other words, you're not allowed to start at 0 and let the left and right hand limits go out to infinity and minus infinity at the same rate and then take the limit. Okay, and there's a very good example that shows why this is true. You just have to look at the integral. In fact, I'll write it down here. So the counterexample would be the integral from minus infinity to infinity of x dx. Okay, so why is this a counterexample? Well, if you integrate from 0 to infinity of x, just think about what the region is going to look like. It's going to blow up an area. You're going to be integrating x squared over 2. So it's going to shoot off to infinity. And the first piece will shoot off to minus infinity. Unfortunately, minus infinity plus infinity is not equal to 0. You should remember that from limits, that you can't just do that. So that shows that this integral diverges. Okay. This diverges by our definition. Part C definition. But if you try and do the limit of t goes to infinity from minus t to t, well, say I integrate from minus 5 to 5 or minus 100 to 100. X is an odd function. So I'm integrating from minus t to t, which is symmetric about the origin, and it's an odd function. That automatically is going to get me 0. So I'm just taking the limit of 0. So converges to 0. The other definition. So if it converges under one definition and diverges under the other, obviously those are not the same definition. Now, this is a very useful definition. It's not saying that you can't do this, but it's different. It's something called the Cauchy principal value, and it's used in a lot of places, and it's very important. But it's just not what we are considering in this class at this moment. Now, the first example that we did, where we integrated 1 over x squared from 1 to infinity, is a special case of a very useful improper integral that we need to look at as just a general thing to remember. And this is going to be really important later when we do infinite series, power series, Taylor series, because it's going to give us a way of determining when certain series converge or diverge by way of when certain integrals converge or diverge. So in that sense, it's kind of a tool. So here's the integral. We're going to integrate 1 over x to the p. So in the example that we had, p was 2. But here, p could be anything, any real number. And instead of integrating from 1 to infinity, I'm going to allow us to integrate just from a to infinity. Now, a lot of books will automatically just say, okay, just 1 to infinity. But I'm going to do it in terms of a, and then at the end we'll say, okay, if a is 1, notice that it matches what's in the book. But I think it's useful just to, if you're going to memorize something, you might as well do it with an arbitrary lower limit instead of just saying it has to be 1. So let's look at this. So there's really 3 cases that are different. So let's look at case 1. So in case 1, we're going to take p to be bigger than 1. So this is very similar to what we did in the example, right? Because we took 2. 2 is bigger than 1. In this case, we're integrating from a to infinity of dx over x to the p, which is going to be the limit. So actually, this part doesn't really depend upon p. And now, how do we integrate 1 over x to the p? Well, let's write it as x to the negative p, because we're going to use the power rule, and if you don't quite see this mentally, it might be a little bit tricky. So it's x to the negative p power dx. When you use the power rule, you add 1 and divide by that. So 1 more than minus p is 1 minus p. So we really get x to the 1 minus p all over 1 minus p. And this is evaluated from a to t. Now, this 1 minus p has nothing to do with t. P is a constant for now. So that's going to be able to come outside the limit. And then when we plug in the lower limit, a, that's also not going to depend upon t. So really, we're just going to get one term that we have to worry about. So let's write this as 1 over 1 minus p all times the limit as t goes to infinity of t to the 1 minus p minus a to the 1 minus p. Again, a to the 1 minus p is a constant. It has nothing to do with t. Only the first term is what we need to worry about. Now, how do I tell whether a power of t is going to blow up or whether it's going to get closer and closer to something? Well, I need to look at the exponent really carefully. So let's look at 1 minus p. In this case, p is bigger than 1. So if p is bigger than 1, that means 1 minus p is less than 0. Right? Another way to say that is p minus 1 is bigger than 0. So if I rewrite this as 1 over t to the p minus 1, maybe now it's a little bit easier to see. This is saying 1 over a positive power of t. Any positive power of t is going to shoot off to infinity. So this whole term here is going to get killed off to 0. So what we see is that we get 1 over 1 minus p times a minus a to the 1 minus p. Now, there's a couple things that can clean this up. The minus sign, we can just switch 1 minus p to p minus 1. And then we want to put the power of a actually in the denominator because then it kind of matches the pattern that we're putting powers in the denominator. So let's go ahead and do that. All right, so we're going to get 1 over p minus 1 times 1 over a to the p minus 1. Okay, so we can write that all in the denominator. It's going to be 1 all over p minus 1 times a to the p minus 1. And this is going to then converge. I should point out, it's written above, but I didn't say it. A is positive here. So a cannot be 0. So I'd be dividing by 0. I also don't want a to be negative. So a is strictly positive. Okay, let's look at the second case. The second case is going to be if p is less than 1. And what we're going to see is that you do the integration exactly the same. All the computations work out the same until you get to the limit. But then when you get to the limit, you notice you got t raised to a positive power. So you don't put it on the bottom, just leave it as t to the 1 minus p. And you're going to say, wait a second, t raised to a positive power, that's going to blow up in my face. It's going to go to infinity. So this is going to diverge if p is less than 1. Okay, so we got the same kind of calculation, but p less than 1, if I subtract p from this, I get 1 minus p is positive. In other words, this is a positive power of t. Well, positive powers of t, sorry, I didn't put the t goes to infinity here. As t goes to infinity, a positive power of t is going to blow up no matter what positive power it is. So this is simply going to be infinity. So actually, to emphasize, plus infinity. In other words, it diverges. So the first case, converge. Second case, diverge. And you say, wait a second. There's one more case left. We did p bigger than 1, p less than 1. Well, the next case is p equal to 1. And why do we have to do it as a separate case? Well, it's because the antiderivative of 1 over x, you can't use the power rule. All the other values of p, you could use the power rule, but we're going to use a different rule now. So let's look at that. If p is equal to 1, then we're just integrating from a to infinity, dx over x. So this is just a limit. T goes to infinity, a to t, dx over x. And since the integral of 1 over x is natural log, this just becomes ln x evaluated from a to t. We don't need to put absolute value here because we're always looking at positive values of x here. But what we do get then is this is the limit of natural log of t minus natural log of a. Now, natural log, it grows very slowly, super slow, but it still goes to infinity. So this is still going to diverge, just like if p was less than 1. So the upshot of all of this is that we only have convergence if p is bigger than 1. That's the best way to remember it. You have to have a power bigger than 1, strictly bigger than 1, in the denominator. Otherwise, it's going to diverge. And here's a nice way to write it. We can kind of put everything together in terms of a. And we could say overall, the integral from a to infinity of dx over x to the p is equal to, so I'm going to do it as a case-wise thing here. So we're going to say it's 1 over p minus 1 a to the p minus 1 if p is less than 1. Sorry, if p is greater than 1, converges, and it's plus infinity if p is less than or equal to 1, meaning it diverges. Now, a lot of the times that you need to remember this, the lower limit is 1, just because that's the way it's set up, or it just doesn't matter that much. So I'm just going to write here, I'm just going to note the case a equals 1 is common. And then I'm going to write down what that gives us here. So that means that the integral from 1 to infinity dx over x to the p is going to be equal to 1 over p minus 1 if p is bigger than 1, and it diverges if p is less than or equal to 1. Check that in the back of your mind. Keep it on file. We're going to use it later in a few weeks or a month or so. What I want to do is do one more example, or actually do a few examples where we're going to use the definition and see if they converge or diverge, and we're going to try to find the value if it converges. All right, and we'll start with this one, the integral from minus infinity to 2 of e to the 3t dt. So for all three of these, if you want to go ahead and pause the video, see if you can work this out on your own, see what you come up with, and then we'll go over it in just a minute. All right, so we're going to go ahead and write this as a limit. So you always want to write it as a limit. Please try not to anti-differentiate and use like a fundamental theorem of calculus and then use infinity or minus infinity as an upper or lower limit. I know there are videos on YouTube that do that, but it's really not the best thing to do because it's defined in terms of a limit. So we really want to be clear in our thinking and use the limit and not plug in infinity like it's a number in the fundamental theorem of calculus. Having said that, if you're very familiar with improper integrals and you've been doing them for years and years and years, you will see people kind of do that as a kind of informal shorthand. That's okay, as long as you really understand the definition and you're so familiar with it that if you could write it out as a limit, you could, and you understand in the back of your mind that that's what's going on. But because you're just starting off, it's probably the first few problems you've ever done of this, it's really important, I think, just to explicitly write it out as a limit and not try and do some shortcut. So we're going to write this out as the limit. Now, normally, I've been using t. Unfortunately, t is the dummy variable here. So we just have to use something else. So let's pick, say, w. There's nothing special about t, so we're going to let w go to minus infinity, and we're going to take the limit, the integral from w to 2 of e to the 3t. This is the limit as w goes to minus infinity of e to the 3t over 3 from w to 2. Again, that factor of a third can come completely outside the limit. So we're going to get 1/3 times the limit as w goes to minus infinity of, let's see, e to the 6 minus e to the 3w. Okay, so you have to ask yourself, what happens to e to the 3w as w goes to minus infinity? Since 3 is a positive number, this is like an exponential growth function, right? So, I mean, I'll just kind of sketch, right? So it's something like this. So we're looking over here as we go out to minus infinity. This is approaching 0. So we're just left with the e to the 6th term. So this is going to be e to the 6th over 3. Moving on, let's look at the next example. This is the integral from minus infinity to infinity. So over the entire real line of 1 over 1 plus x squared. So see, whether you think this converges or not, take a minute to do this. And even though it doesn't depend what number you choose, there's a number that's most convenient here, so you might want to choose that one. So go ahead, see what you get here, whether it converges or diverges, and if it converges, what value. Okay, so the most convenient number to split this up here is at 0. And in fact, 0 is one of the most common numbers that you would split up one of these integrals. Not just because 0 is a nice number, but because it often works well with the integrands. So we're going to do the same thing here. You might also notice, just kind of intuitively, this is an even function. So if we split it at 0, whatever we're gonna get for one of them, we're going to get the same thing for the other one. I'm not going to assume that. I'll go through and calculate it, but that ends up being the case. Okay, so we'll do each separately. The integral from minus infinity to 0 of this is the limit as t goes to minus infinity. We're integrating t to 0. And you have to remember that this is inverse tangent. So it's inverse tangent from t to 0. Whoops, I didn't write the t. Oh well, you know what I mean here. So this is the limit as t goes to minus infinity of inverse tangent of 0, which is 0 minus inverse tangent t. Now you have to know a little bit about the inverse tangent function. If you think about that graph, remember that it has two horizontal asymptotes. It starts at 0 here, and it goes up to this horizontal asymptote, and then this way it goes down to this one. And those are at pi over 2 and minus pi over 2. So we're going out to minus infinity, so this is going to be the limit as we go out to minus infinity is going to be minus pi over 2. However, so obviously the 0 goes away, but it's minus that. So it's minus a minus pi over 2, which is pi over 2. And similarly, the integral from 0 to infinity, I'll kind of skip a couple steps here. This is the limit as t goes to infinity of inverse tangent t minus 0. And inverse tangent goes to pi over 2, so that's pi over 2. So putting them together, adding, we see that the integral from minus infinity to infinity is equal to pi over 2 plus pi over 2, which is pi. So the area under the graph of the function 1 over 1 plus x squared and above the entire real line, so that whole infinite extended region has area exactly equal to pi. Kind of remarkable fact. All right, we're going to look at one last one. The integral from 0 to infinity of cosine x dx. So again, pause the video, see what you get with this, but maybe before you even start the calculation, think about the graph of cosine. make an intuitive guess about whether you think this is going to converge or diverge and what it might converge to if it does. You might be able to just kind of guess what the answer is going to be without actually doing the calculation. Now, after you do that, you should do the calculation, but try and think about it first. All right, so here's hopefully what you should have gotten. This will be the limit as t goes to infinity of integral from 0 to t cosine x dx, which is the limit t goes to infinity. The integral of cosine is sine. So we're integrating sine from 0 to t, which means we get the limit as t goes to infinity of sine of t minus sine of 0. Now, sine of 0 is 0. So that just goes away. So really, we're just looking at that term. What happens to sine of t as t goes to infinity? Again, consider the graph. So the graph of sine is always between 1 and minus 1. And it oscillates, right? It's always going back and forth. It's a sinusoidal function, right? So this is going to oscillate forever, no matter how far out we get, as t goes to infinity. So this limit is going to diverge. So it does not exist. So I'm just going to say diverges. But it does not diverge, like the 1 over x to the p that we saw before that diverged to infinity. This one just diverges. And that's just all we're going to say about it, is it just doesn't converge. All right, so that's a few examples of these type 1 improper integrals. In the next video, we're going to look at the second type, which is where the integrand has some problems. The function itself has a problem that it's blowing up to infinity or minus infinity or maybe both, depending upon the direction. And we'll go over how we handle that type of improper integral in the next video.